Hello navigators, welcome back. Today we are going to talk about heat conduction. Basically how we can solve heat conduction problems in OpenFOAM. Heat conduction is a diffusion problem where the heat flows from high value of the temperature to low value of temperatures. In order to solve heat conduction problem, we can use Laplacian foam that is present in OpenFOAM solvers, and this is the easiest way to getting started with heat transfers in OpenFOAM. Let's get started. I have opened here the source code for Laplacian foam. Here, in order to explain that how we solve this, you can see here that it solves basically this equation, which is the rate of change of temperature is equal to divergence of dt times grad t. That means basically if dt is constant, then it's the Laplacian of the temperature, where t is the scalar field. Here we are concerned about temperature, but in case you want to solve something else using this particular solver, you can also solve this. Therefore a general name is used, a scalar field here, and dt is a diffusion coefficient. Here it's going to be alpha in case of heat conduction. The solver is also straightforward. Here is the simple loop. In the simple loop, you first create this equation, which is nothing but d dt minus Laplacian of this thing, which is equal to any source term if you want to add. So FE options can be used to add any source term, and then after constraining this equation, then you can directly solve this, and then you can correct this t using any options that you have passed through FE options. Now let's see how we can use this to solve a problem where we'll take a geometry that we have been taking so far, which is a square, and around that we have a domain. Let's get started. Here I have created a folder, LabFoam. Here you can see that this is an example from a rotating zone. I'll first remove this rotating zone and keep this square only, and then we'll see that how we can set up a boundary condition for this. We just need to add a temperature value here at this boundary, and everywhere else we'll keep the value as say 300 here and 600 here, and then we'll see a gradient that will be forming here. Let me first clean this. In the snappyHexMesh, I'll first remove this. We don't need this rotating, and let's find rotating anywhere else. This one also not required anymore, and here also it's not required. And we'll also not use any refinement regions. I have commented this one as well. And then in the boundary, we just need temperature. I'll rename this as temperature, remove this, and remove all other files. Here temperature is, we know that this is M L T, then this should be temperature. I'll confirm this should be 0, this should be 0, and then we'll say that this is uniformly 300 everywhere, and at the cylinder it's something else, which is fixed value. The type is fixed value, and the value is 600, and the sides are empty. Bottom we can keep them as 0 gradient, and at the outlet we'll keep a fixed value as 300, which is same as here, fixed value, but the values we have changed. We don't have any AMIs anymore, and we just need this much. Now next thing is, in the block we have to create this mesh again. Let me run blockMesh, then snappyHexMesh. Here we can see that the mesh that we have created it looks something like this. We may need more number of layers, that we will see when we are solving. Now let's set up other things. We just need to set this first, that our transport property is just dt as we have seen previously, and let's keep the value 4e minus 5, and these two we don't need, we can comment these. And the turbulence property we don't need. Let's rename this to this dot old, and we also don't need this dynamic mesh. This is also dot old. Then in the controlDict, let's rename this to LaplacianFoam, and the time step and all you can keep this, because we are going to use a simple method, therefore we don't need this time step criteria, because the stability will be controlled by the relaxation parameter that will set in the solver. In the fvScheme, we'll need a bunch of stuff. Let's see what we need. You can find these from different examples that are present in OpenFOAM tutorial, but you can also find this by running it once and then find what is not available, then just fill those keys. We'll need this, and SN grad, we don't need any overset interpolation. This is an example from overset method, therefore it has this. This we are not going to keep orthogonal, we'll use corrected. And let's see what else we need. This should be steady state. Now this is not steady state because this has a ddt term in the solver. You can see here we are solving for this, which has a ddt term. Therefore this is not a steady state problem, as I was saying before. And in fvSolution, we have to solve for temperature instead of pressure. Let's use a multigrid solver only and solve for temperature, and everything else is not required. It's a simple solver. Probably it will ask for some parameters for simple, that we can see later. We are going to have this relaxation parameter set to 1 for now, and let's try solving with these parameters. We'll say Laplacian. So something is missing here. It should be uniform, so we mix this parameter. This should be uniform, and here also it should be uniform and uniform. Now let's see again. This is empty, but here, as we know that this patch cannot be empty when we are using snappyHexMesh, we have to manually make this patch empty. And then let's try solving. It is solving. Let's see, it has solved for few time steps. Let's see the results. Here you can see dt term, which is constant because it is not changing. It may change with temperature as well, that's why this is an output. Then let's see temperature. Temperature has this kind of a gradient. That means we have to increase the diffusion, so we should do this as say 0.2 and then try with this. Now let's see the results. Clearly now we can see better diffusion, and with time this also grows. We can see that there is a clear gradient, and as time progresses this temperature is diffusing everywhere in the domain. With this we have learned that how easily we can do a simple diffusion of any scalar quantity, not just temperature. We just need to calibrate the coefficient of diffusion in order to match the real life values of this. With this we'll stop, and in the next lecture we'll talk about that how we can combine this heat transfer with fluid flow, and with that we'll be able to solve more complex multiphysics problem where we'll solve in the solid how the conduction is taking place, and then within the fluid how convection is taking place, and then how overall heat transfer is taking place between solid and fluid. That all we can model in OpenFOAM. See you in the next lecture.
Thanks for watching, and if you like the content of our channel, then please like, comment, share and subscribe.